Let's talk about periodic properties of the elements. First I'm going to cover is electron configuration. Electron configuration of an atom is a particular distribution of electrons among available subshells. The notation for configuration lists the subshell symbols S, P, D, and F sequentially, with the superscript indicating the number of electrons occupying that subshell. For example, lithium, with atomic number 3, has 2 electrons in the 1s subshell and 1 electron in the 2s subshell, making its electron configuration 1s2, 2s1. Ground state configuration refers to the most stable, lowest energy way of assigning the electrons. All other ways are higher energy or excited state configurations that are unstable and caused by absorbing light or collisions with other particles. Excited atoms eventually revert to their ground state configuration either by giving off light or as a result of collisions with other particles. If ground or excited state is not specified, we assume the term electron configuration refers to the ground state. Let's see what the maximum number of electrons allowed per subshell based on Pauli's exclusion principle. That is, you can have no more than 2 electrons in any one orbital. For the subshell of S, L equals 0, if you recall from the previous section, you have 1 orbital. Maximum of 2 electrons per orbital means the most we can have is an S superscript 2. P, meaning L equals 1, there's 3 orbitals, you recall, -1, 0, and +1. Therefore, 2 per each orbital means a maximum of 6. So, the highest superscript on P would be P6. D, L equals 2, 5 orbitals. 2 in each means a maximum of 10 electrons can be in the d orbital, so d10 is the max. F, 7 orbitals, with 2 in each orbital, means there's 14 maximum, so the highest F superscript you can have is 14. The Aufbau principle is a scheme used to reproduce the ground state electron configurations of atoms by following the building up order. Listed below is the order in which all the possible subshells fill with electrons. Starting with the lowest energy, we have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, where these are the highest energies. Now you don't have to memorize these because the periodic table pretty much tells you how to do this, and we'll talk about that in a few minutes. This order is based on increasing energy levels using the following factors. Orbitals with higher n plus L values have higher energies. Example, 3d. N equals 3, D equals 2, add that up, I get 5. That's higher in energy than a 4s because N equals 4 plus 0 for the S equals 4, because the N plus L value is higher. Note D, L equals 2, and S, L equals 0. For orbitals with the same N plus L values, the orbital with the higher N will have the higher energies. Example, a 3s. That's 3 for the N and 0 for the S. That's a 3. Has the same N plus L value as 2p. That's 2 for the N and 1 for P, giving it a 3. So both have 3. But the 3s is going to be a higher energy because of the higher N of 3. That's why we have 3s, above the 2p. And in the previous example, that's why we had 3d higher than 4s. Here's your periodic table. The periodic table allows you to do the electron configurations without having to memorize all those levels. we can use the periodic table as a memory aid for the typical ordering and filling orbitals. These first two columns are your S blocks, and one orbital with a maximum of 2 electrons. So you can have a total of an S2. So we basically count each block as S1, S2. Except for helium, which is over here, we have in the first row S1, and this would be S2. Here is your P block. Okay, maximum of 6 electrons. Basically, each one of these blocks counts as one of the P6s. P1, P2, P3, P4, P5, P6. The D block is right here. Remember, the D block had 5 orientations. -2, -1, 0, +1, +2. 2 electrons per each orbital. That's a total of 10 electrons maximum. D1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F block, you may recall, had 7 orbitals, meaning 14 electrons each. F block 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you're pretty much just going to read across the periodic table, putting in your electron configuration so you get to the block of your element in question. Now some points to make up to state here. Notice that we build in increasing 1s, 2, 3, 4, we increasing, but right here, the D block is 1 level less. Okay, so even though we start off at 4s, when we start our D block, we start off at a 3D. 1 less. Same thing right here. See this star? All this for the 4Fs go right here before you get to that next D block. So here's 4D, 5D, 6D. Right here, your 5D2. You're going to go from 5D1 and do all the F block before you do 5D2. Same thing for your 6D. Double star, you coming down here. Now notice that we start off with 4F, which is 2 less than your period. So this starts off as 4F1, 4F2, etc. Okay, so you're 2 less for your F block. So, to write the ground state electron configuration of an atom, you first need to locate the atom on the periodic table. For a neutral atom, the number of electrons equals the number of protons, atomic number. You write the subshells with the number of electrons in the subshell written as a superscript, N, L, to the sum number of electrons, from left to right and top to bottom until you reach the particular atom in question on the periodic table. Basically, each block represents an electron that you'll be adding to the configuration. So, let's look at scandium, number 21. Okay, that's atomic number 21. That means it has 21 electrons to account for in its electron configuration. Whereas scandium, it's right there in the first D blocks. So what we're going to do now is name our pure electron configuration starting from the top, go all the way through, accounting for every one of these blocks till we hit the element in question. So, first we got 1s2. I'm going to go through 1s1, 1s2, so that's complete. Then we go through this, 2s1, 2s2, that's complete. We're going to go through 2p1, 2, 3, 4, 5, 6. So 2p6 is complete. We'll go through 3s1, 3s2. That's complete. We'll go through 3p1, 2, 3, 4, 5, 6. That's complete. We'll go through 4s1, 2. That's complete. Then we move into the Ds. Remember, this is 1 less. The Ds start off 1 less than the period it's in. So that ends up being 3D1, which is the electron configuration for scandium. So the ground state electron configuration for scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Another example, boron. Boron 5 is right here. In the third column, we have 5 electrons to account for. So we'll go through this. So we go through 1s1, 1s2. So it's 1s2. We go through the 2s2. And now we're going to go into one of the 2p's. So 2p1. That's the electron configuration for boron. Let's try neon. Where's neon? Neon is right over here. Okay, the last one on the second period. Well, we go through 1s1, 1s2, go through 2s2, go through all the 2p's, ends up being 2p6. Sodium 11, right there. 1s2, 2s2, 2p6, 3s1. Lead 82, way down here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now remember, the D's are one less than the period it's in, so we start 3D10 all the way through. 4p6, 5s2, 4d10, 5p6, 6s2. Remember this little star, that means I go down to the F block here, and remember it's 2 less than the period it's in. So in this case, I got to go here, and I'll do my 414, 4f14. Then I go back up and do my 5d10, and then I'm into the P's by 2 of them. 6p2. There is a short notation for writing electron configurations, which involves using a noble gas core. Remember, the noble gas is over here on the far right. We specify the noble gas in the row above the atom in question in brackets, representing the electron configuration to that point, and then write the configuration of the remaining electrons. For the above lead example, we would write, well, in essence, we're talking about here's lead. So we're talking about right here, that block right there, we're going to go take all that and put that in brackets, what that element is, which happens to be xenon. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, all that. Instead of writing all that, I can write the element of xenon, put it in brackets, and then finish the electron configuration. The 6s2, the 4f14, the 5d10, and my 6,2p. There are exceptions to the order of filling electron configurations, okay, where it doesn't go as it flows on that periodic table. Notably, those exceptions are listed right here. Now, the ones that you mostly got to be concerned about would be chromium, copper, and silver would probably be the ones you most likely run into. The commonly used justification for these exceptions is that the electrons are shifted in order to have half-filled D5 or fully filled D10s. So in a D block, they tend to try to be more stable by having a half-filled arrangement. So they take electrons from the outer shell, like the 4s, take one of those and upload and put it in the D block to get a half-filled or full-filled shell. There seems to be some stability attained with half-filled and fully filled subshells. But this justification is tenacious since the exceptions are not consistent. Example, copper. Argon 3d10 4s1 is the actual electron configurations instead of what you would predict by following the periodic table of 3d9 4s2. What happens here is it promotes one of these electrons up to the 3d level to get that full shell, and the d's, since it's an inner shell, that tends to be a little bit more stable. One electron has shifted from the s orbital to the d level for the stability gained from having the inner shell completely filled. Valence electrons are electrons that reside in the outermost shell of the atom, and in other words, those electrons outside the noble gas core. These electrons are primarily involved in chemical reactions. Elements within a given group, that's your vertical column on the periodic table, have the same valence shell configuration. This accounts for the similarity of the chemical properties among groups of elements in the same family, meaning a vertical group. Example: phosphorus, arsenic, and antimony are all in the same group, same column. Notice what their electron configurations. They all have an S2 block filled, and they all have a P3 filled. Now the 3d10 and the 4d10, those are inner electrons and do not count as valence electrons. It's only your outer, your S block and your P block is what you're looking at there. These three atoms reside in the same group 5A and have the same valence electrons, 2 in the S block and 3 in the P block. Therefore, they react very similar and have similar properties. Valence electrons for the groups. Group 1A, that's that first column, tends to be NS1. Group 2A tends to be NS2. Group 3A, that's jumping past the transition metals, okay, your main group elements, NS2 and NP1. Group 4A, NS2, NP2. Group 5A, NS2, NP3. Group 7A, NS2, NP4. Group 7A, NS2, NP5. And Group 8A, NS2, NP6. Now what about the transition metals? Transition metals tend to be an NS2, N-1, remember it's one level less, D to the X, where X could be 1 to 10. So for scandium, you have arsenic 4s2, 3d1, so in essence, your valence shell is 4s2, 3d1. So far we have done ground state electron configurations for neutral atoms. What happens if you have an ion or a charged atom? Since we are counting electrons, any charge will either add or subtract the number of electrons we are placing in the electron configuration, meaning the number of electrons does not equal the number of protons. For cations, we will subtract electrons from the total. Calcium 2+, that means I have 2 more protons than I have electrons. Okay, so we're going to subtract 2 electrons because you have lost 2 electrons. For anions, we will add electrons to the total. Chlorine minus. This tells us we have 1 more electron than we have protons. So we have to add 1 and we gain an electron. A few examples. Calcium. Its electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We have calcium 2+. What we have done is we drop the last 2 electrons, the 4s2, and we end up with 1s2, 2s2, 2p6, 3s2, 3p6. We lost those 2 outer shell electrons, which makes sense because what's trying to happen, what the species is trying to do, is trying to get a noble gas configuration. It wants 8 electrons in its outer shell. That is the most stable. So it's easier for it to lose 2 than it is to gain 6 more and get that. So it tends to lose those 2, and that's why we have our cations losing electrons and we have our anions gaining electrons, because it's easier for them to gain it than it is to lose it, as you see in the next example. So like chlorine, you got 1s2, 2s2, 2p6, 3s2, 3p5. It's 1 electron away from having an octet. So it's going to be easier for chlorine to gain 1 than to lose 5. So it tends to do that, and that's why it becomes a negatively charged ion. So then it gains the 1 electron, which then gives it 3p6, and now it has an octet. It has 8 electrons in the outer shell. Now notice something between calcium 2+ and chlorine minus. They have identical electron configurations. We can throw in one more, argon. Argon also has the same electron configuration. So you have argon, calcium 2+, and chlorine minus all have the exact same electron configuration. We say that these species are isoelectronic with each other. They have the same arrangement of electrons, but are not the same species. That doesn't make calcium 2+, chlorine minus, and argon the same thing. They just happen to have the same number of electrons, same electron configuration. However, they have a different number of protons, which is where their identity comes from. Okay, each one of those still have the same number of protons that they had before losing electrons or gaining electrons. Electrons do not come off the same way they go on. The outermost valence electrons come off before any inner electrons. So the higher energy levels come off before any inner electrons will come off. Example, look at vanadium. You got argon 4s2 3d3. And we're looking at vanadium 3+. These 3 electrons are going to come off. They're going to have to come off on the higher energy levels first, before we take off any inner electrons. So that means the 4s2s are going to come off, and then 1 of those 3ds, which gets us argon 3d2. So in this case, we lost 3 electrons, the 2 outermost 4s and 1 inner 3d. Note, we did not lose all 3 in the d level. We lost 2 from the s2, from the 4s2, and then 1 from the 3d. An orbital diagram gives more detailed information than electron configuration. In an orbital diagram, electrons are represented by arrows. Boxes, circles, or blanks are used to represent orbitals. Upward pointing arrows represent electrons with +1/2 spin, and downward pointing arrows represent electrons with -1/2 spin. Pauli's principle must be followed, meaning no more than 2 electrons per orbital with opposite spin. We fill the orbitals in the highest occupied subshell singly with electrons of the same spin before putting a second electron of opposite spin in any orbital. This is known as Hund's rule of maximum multiplicity. The justification for Hund's rule is spin correlation. Electrons with same spin repel each other less than electrons with opposite spin. An orbital diagram is used to show how the orbitals of a subshell are occupied by electrons. Each orbital is represented by a box, a circle, or a line. Each group of orbitals is labeled by its subshell notation. For example, down here I have a 1s, a 2s, and a 2p. Remember in previous chapter that the 2p's had a -1, a 0, and a +1 orientation. That's what the 3 circles represent. Notice in this particular notation, there's no distinguish of energy levels. They're all on the same level. Electrons are represented by arrows, up for ms +1/2 and down for ms -1/2. We fill the orbitals in the highest occupied subshell singly with electrons of the same spin before putting a second electron of opposite spin in any orbital. Let's look, for example, at neon. We have 10 electrons to account for. So we would put 1 up in the 1s orbital. Then we would fill in the complete any particular orbital first, any energy level first. So in this case, I would come back with a second spin pointing down. Then I'll do the same thing with the 2s. I have 1 up and then 1 down. For the 2p's, I'm going to have to fill up one in each one of the orientations before I come back and pair them in opposite spin based on Hund's rule. So my first one would come in one of the orientations. Then my second one would come pointing up again in the second orientation. And then the third one. Then I would come back and start pairing. And this is my 9th electron, and my 10th electron ends up pointing down in the third orientation of the 2p's. Here's another way orbital diagrams are displayed by increasing energy levels. See, we have our energy levels pointing up. So we know 2s is greater than 1s, 2p are greater than 2s and 1s, etc. Notice the 2p's, as we stated earlier, or have the same energy, so they're all at the same level. 3p's at the same level, and the 3d's are all at the same energy level. For this example, we're going to do vanadium, which has 23 electrons to account for. So we'll fill one up, one down for 1s, one up, one down for 2s, one up again, and a third one up for the 2p's. Then we come back and pair, one down, and one down. Then we do the 3s, one up, one down. 3p's, we'll do them singly up, and then pair them down. 4s, one up, one down. We have 3 more electrons to count for, so we put them one up, and one up. That is the orbital diagram for vanadium. Now notice that I have 3 electrons that are unpaired in that D level. We're going to bring this up again coming up in the next slide or two. The maximum number of electrons in the orbital diagrams are as follows. The S block, you have 2 electrons to count for, so there'd be one circle with 2 electrons, one up, one down. For the p orbitals, we have 3 orientations, -1, 0, +1, so you have 3 up and 3 down. For the D block, you have 5 orientations, so you have 10 electrons, 5 up, 5 down. And for the F block, you have 7 circles, so you have 7 up and 7 down. Although an electron behaves like a tiny magnet, 2 electrons that are opposite in spin cancel each other. Only atoms with unpaired electrons exhibit magnetic properties. Paramagnetic substance is one that is weakly attracted by a magnetic field as a result of one or more unpaired electrons. Whenever the electron configuration of an atom has partially filled subshells, the atom is paramagnetic. If you just recall, vanadium on slide 17 had unpaired electrons in the 3D level. We had 3 electrons that were unpaired. Therefore, vanadium is paramagnetic. Diamagnetic substances is not attracted by a magnetic field because it has only paired electrons. If you recall, neon on slide 16 had all electrons paired. Therefore, it is diamagnetic. Homework 61 to 62.